Today I'm going to introduce our work about Hennessy-Milner results for probabilistic PDL. The structure of the talk will be as follows. First, we will recall some background knowledge about PPDL and Hennessy-Milner properties. Also, we introduce some of the related works and our motivation. Next, we will see the characterization results of PPDL. After that, we go on to introduce two notions of bisimilarity and see that two extensions of PPDL characterizes these two notions. Let's first have a look at the subject of our paper, namely probabilistic propositional dynamic logic, also known as PPDL. It was first introduced by Dexter Cousin in 1985 to reason about the probabilistic programs at a propositional level. So instead of problems like the determination of a program, PPDL describes properties such as what is the expected running time of a program involving coin flipping. Such demands determines that the nature of the logic must be real-valued rather than Boolean-valued. We will come to more details about PPDL later, and before that we introduce some knowledge about Hennessy-Milner properties. Hennessy-Milner properties are basically bridges between logical equivalence and structural similarity. The benchmark work is traced back to Hennessy-Milner's paper in 1985, in which they proposed a simple model logic characterizing bisimulation for image finite label transition systems. The importance of such properties is that once we have the bridge between logical equivalence and structural similarity, then in order to check that two structures are not behavioral equivalent, one can simply do it by finding a logical formula which distinguishes the two models, and this is usually much easier than the former work. Our paper is based on many previous work on labeled Markov processes. Labeled Markov processes are continuous probabilistic transition systems, and as one will see later, they are basically PPDL models without the function valuations. We apply both the results and some proof techniques in the first three papers listed here. There they proved that a simple logic L0 characterizes both state and event bisimulation between labeled Markov processes. Other related work also mostly considers labeled Markov processes. For example, this paper here gives a real-valued logic, which gives the same Hennessy-Milner properties for labeled Markov processes. However, as far as we know, there's no Hennessy-Milner results for PPDL and behavioral equivalence for PPDL models. So the first question we ask is that what behavioral equivalence does PPDL actually describe? After this, we defined the state and event bisimulation for PPDL models, which we think are natural extensions of that for labeled Markov processes. We then try to extend PPDL in a natural way such that the new logics characterize these two notions of bisimulation. Finally, we take this paper as the first step towards further research on Hennessy-Milner properties about coalgebraic dynamic logic. Alright, we are now ready to introduce our first characterization result, namely PPDL characterizes trace equivalence. Before that, we briefly talk about PPDL. The syntax for PPDL is fourfold, and we only present the non-trivial parts here, namely the programs and the functions. The programs involve primitive programs, sequential composition, and Boolean tests. Besides, it have arbitrary linear combination and iteration. For the functions, the most important part is the modalities, namely diamond P, F in green here. So this syntax is rich enough to express programs like while loops and conditionals. As for the semantics, a PPDL model is a tuple where sigma x here is a measurable space, Vp and Vf are respectively valuations for primitive programs and primitive functions. Programs are interpreted as Markov kernels here, which are basically probabilistic state transition functions. And function symbols are interpreted as real-valued functions. In particular, the value of diamond Pf is the expected value of function f after executing program P. Next, we introduce the notion of trace. The terminology trace comes from automata theory, and our definition of trace on PPDLs is actually a natural generalization of that for probabilistic automata. For the alphabet set, we have not only the primitive programs, but also those Boolean tests. The reason, put it simple, is that Boolean tests also appear as primitives in the formal construction of PPDL programs. Then the trace rho at a state x is a function which takes two inputs, a word omega in sigma star and the primitive function capital F, and then it returns the expected value of function f after the transition omega starting from state x. We illustrate our definition through a simple example here. So the primitive programs are A and B, and we only have one function symbol f. The states with a red circle are states whose value of f are 1, and the rest all have value 0 for f. One can simply calculate that the trace at x0 with inputs a, b, and f have value 1 over 2 times 1 over 3 times the value of f at x2, which is 1 over 6. Similarly, one can calculate the trace of y0 with the same inputs. And since these two values are different, we say that these two pointed PPDL models are not trace equivalent. In fact, one can notice that these two pointed models are also distinguished by some PPDL function. For example, diamond A then B, F. Notice that this PPDL function looks very similar as the input of the trace we had before. So this somehow already implies one direction of our characterization result. Namely, PPDL equivalence implies trace equivalence. The non-trivial part here is that the relatively seemingly weak notion of trace equivalence actually implies PPDL logical equivalence. And this is based on the following observation that the diamond somehow distributes, the linear combination somehow distributes over the modality here. And this will give us our first theorem, namely PPDL characterizes trace equivalence. Next, we go on to states by simulation and event by simulation. We first have a look at state by simulation, which is more intuitive. So let's start from state by simulation between labeled Markov processes. So labeled Markov processes, as shown here, is simply a measurable space together with some transition functions on it. And a labeled Markov process state by simulation is a binary relation on the state set such that for any R-related pair x and x prime, and for any R-closed subset A of x, the transition, the probability of x transit to A and the probability of x prime transit to A via program P are always the same for any primitive program P. This is illustrated by the figure here. So this y r1 prime and z r z prime illustrates the meaning of A being R closed. Namely, for any R related pair y and y prime, either both of them are in A or both of them are out of A. This notion of state by simulation is actually very intuitive in the sense that they are very like the notion of bisimulation in the classical case between labeled transition systems. The only difference here is that the reachability condition now is replaced with the probability of the transition. For the state bisimulation between PPDL models, since PPDL models are basically labeled Markov processes with this red extra valuation on primitive functions, we can define state bisimulation between PPDL models naturally by taking into consideration this extra weight structure. So we say that besides the above conditions, we require a state bisimulation. We require that for R to be a state bisimulation, any R-related pair should have the same value on any primitive function f, which is illustrated by the red part here. We also illustrate this by a simple example. So here we also have two discrete PPDL models. The states with red circles have value 1 for f, while the red states have value 0. We claim that the states x, x0 and y, y0 are not state bisimilar. This is basically because if we do want to have a bisimulation relation R, which relates x0 and y0, then we indeed want to relate x1 with y1 and x2 with y1. However, this is not possible because, for example, y1 can transit to state y3 via b, where y3 has value 1 for f. But for the state x2, via program b, it can only transit to state x4, whose value of f is not 1. This simple argument tells us that x0 and y0, there's no bisimulation which relates x0 and y0. However, one can calculate that actually these two pointed models are trace equivalents. This implies that state bisimulation is actually a strictly stronger notion than trace equivalence. And furthermore, it implies that in order to characterize trace equivalence, and in order to characterize state bisimulation, we do need to strengthen our logic, namely PPDL. The notion of state bisimulation, it has some shortcoming, namely it requires analyticity, even just between labeled Markov processes. So our idea comes from the simple logic L0, which characterizes state bisimulation for labeled Markov processes. So this simple logic L0 is defined here, whose key part is the yellow part. The yellow part basically does a threshold check. It says that if it says that the probability to be transferred to a state which satisfies phi via program P is bigger than the value R. R is the number between 0 and 1 here. So since it characterizes state bisimulation for labeled Markov processes, and our notion of state bisimulation between PPDL models are kind of natural extension of that for labeled Markov processes, we imagine that if we could add L0 somehow to our PPDL, then our new logic should be able to characterize this new notion of state bisimulation for PPDL models. The difficulty here is that L0 is a Boolean valued logic, while our PPDL is essentially real valued. So what we did is that we simply add a new constructor bigger than R for our PPDL Boolean functions, And then we can express the yellow threshold check via the new PPDL plus function in green here. Essentially, it says that after executing P, the expected value of function f is bigger than r. And since f here basically denotes the formula phi, so the green part basically does the threshold check, as we said before, for the yellow part. And here we have this new logic PPDL plus, and one direction is kind of easy, namely state bisimulation implies logical equivalence. The non-trivial direction here is PPDL plus equivalence implies state bisimilarity. We solve this by using some proof techniques which they use to prove that this L0 characterizes a state bisimulation. And this gives us our second theorem, namely PPDL plus characterizes state bisimilarity for PPDL models. Finally, we come to the event bisimulation. So the notion of event bisimulation is a bit more involved than the notion of state bisimulation, because it is no longer following the idea of state-to-state transition. Spelling out the definition, and if we still start from labeled Markov processes. So a labeled Markov processor state event bisimulation is a sub-sigma algebra of the measurable space on X, such that if we replace sigma X with lambda, the new tuple we have is still a labeled Markov process. This definition comes from the observation that for a relation to be R to be a state bisimulation is equivalent to having this tuple to be a labeled Markov process, while this sigma R is the sigma algebra generated by the binary relation R. This notion of event bisimulation is interesting because it has several advantages over state bisimulation. First of all, perhaps one of the most important one is that the characterization, it no longer requires the analyticity requirement. For state bisimulation, this is necessary in order to prove that state bisimulation has transitivity. But for event bisimulation, this is no longer a problem. And secondly, from a categorical point of view, this notion of event bisimulation arises naturally from cospans. Our notion of event bisimulation is also kind of natural extension of that for labeled Markov process by taking into account the evaluation for primitive functions. So apart from being a labeled Markov process event bisimulation, we require that this sub-sigma algebra lambda to be compatible with our evaluation, in the sense that the inverse image of any value is still an element in this new sigma algebra. So in order to find an extension of PPDL which characterizes this new notion of event bisimulation, we still go back to L0 characterization results. So the previous L0 not only characterizes state bisimulation, but also characterizes event bisimulation for labeled Markov processes. So somehow our PPDL sharp should also express the threshold check, but since event bisimulation is somehow a relatively weak notion of bisimulation, our logic PPDL plus turned out to be too strong to be invariant under such bisimulation. So we need to add this threshold check in a more restricted way. There are more than one solution, but what we did is that we allowed only new functions of the form diamond P B bigger than R, rather than arbitrary F on the left-hand side, where B is a Boolean function. so that we avoid over complicated structure on the left hand side of this constructor. This, and using some proof techniques of the L0 categorizing results, we can finally show our third theorem, namely the PPDL sharp categorizes event bisimilarity for PPDL models. Now, to summarize, in our paper, we first proved that the original PPDL categorizes trace equivalence for PPDL models. After that, we go on to introduce states and event bisimulation based on the notions for labeled Markov processes. These two notions, I think, are quite natural and reasonable generalization. And finally, we extended PPDL by incorporating those threshold check in the L0 and give categorization result for these two notions of bisimulation for PPDL models. So after that, we have the future work. First of all, we do need to check some computational properties of our extended PPDL logics. For example, does this do have a small model property, and what is the complexity of doing, for example, model checking on it? And second, we have a bigger plan of trying to prove some Hennessy-Milner style results for generic coalgebraic dynamic logic. So coalgebraic dynamic logic was proposed partly to prove the completeness of game logic. And actually, it is a very generic picture which includes PDL, PDL with neighborhood semantics, and also this PPDL. We have already some primitive results. For example, if certain distribution properties like this hold in coalgebraic dynamic logic, then our proof for trace equivalence of PPD, our characterization for trace equivalence can actually work to prove that these logics also characterizes trace equivalence. Besides, we have also shown that certain notion of bisimulation always preserves logical equivalence of coalgebraic dynamic logic, while the inverse is obviously not true. For example, bisimulation between PPDL models. For example, PPDL equivalence does not imply states nor event bisimulation between PPDL models. So this is basically the bigger picture that we try to do, and this paper is definitely the first step towards such a goal. Thank you.